Science Uncut, presented by the Volkswagen Foundation.
My title is Risks and Benefits of Potential Pandemic Pathogen Creation. How should we evaluate them and what alternatives exist? That's a long title, and I will not go into all of these in great detail. But there's been some talk already in this meeting about the idea that that risks and benefits are fuzzy and that it's very hard to weigh them. And I want to disagree with that and provide an example of how I think the risks of this kind of work that we're discussing today can be quantified approximately, maybe not as a precise value, but as a range of values where even the lowest value in that range is incredibly concerning and not something we would want to accept. And then I want to talk about the benefits, where I think talking about the benefits of science in general is very, very difficult. Talking about the benefits of allocating between a particular small class of experiments, as Yoshi described, gain of function in flu, gain of function of concern in flu, and the coronaviruses in the United States is 18 studies out of a over $2 billion budget for the infectious disease part of NIH. So we're talking about a very few number of experiments, and we could reallocate that money to something else. So we're not talking about censoring the amount of science that's done, or even censoring a particular type of question being asked. We're talking about how we should allocate within the constraints of a scientific budget, and that's something we do all the time as funders and indeed as principal investigators managing our own work. So that's going to be my basic theme. A couple of disclaimers. These are my own views and not those of my funders who have kindly supported work on pandemic risk or necessarily others or my institution. Lynn Klotz has and Ed Sylvester have coined the term potential pandemic pathogens, which I think is the best of many flawed terms for summarizing the particular class of experiments that Yoshi also correctly described as gain of function of concern. That might be the best alternative definition or term. And has also described several, those two have also described several calculations similar to those that I will talk about. And the last point I want to make really arises from the debate that's arisen in the United States on, occasioned by the funding pause, which to some people's surprise, including mine, included not only influenza gain of transmission experiments, but also experiments on gains of pathogenicity in coronaviruses. I don't know what the risk-benefit profile of those are. It took me by surprise that that was even on the list. I want to leave open the possibility that those experiments have a very different set of risks, possibly lower, and a very different set of benefits, possibly greater. So I think it's going to be very important in all of the discussions to be specific about the category of experiments we're talking about. In English, but not in German, there are two words, biosecurity and biosafety. As I understand in German, they're the same word. And I want to make the distinction. I think most of you understand it already, but biosafety has to do with accident risk, and biosecurity to do with the risk from malevolent use. Initially, many people looked at the studies we're talking about today in the context of biosecurity, but now the concern has largely shifted to biosafety. These are connected ideas, but really distinct, and I'm going to focus on biosafety. The first point I want to make is that enhanced transmissible flu viruses are nearly unique in their combination of hazardous properties, yet are not currently worked on under conditions commensurate with the risk they present. They have high virulence, pandemic potential, and they do not yet exist in nature. And they're handled at the moment primarily in biosafety level 3+. Work on viruses that are less transmissible but have high virulence and already exist in nature is performed in higher containment laboratories, biosafety level 4. And work on a virus that is similar, in my view, to has similar properties, in my view, to those of the enhanced flu viruses. Smallpox is done in 2 laboratories around the world with tight restrictions on the sorts of science that can be done, which everyone accepts. If you're in Germany, you can't do any work on that. On that virus. If you're anywhere outside of Vector or CDC, you can't do any work on that virus. We accept that because of the biosafety and public health concerns, and indeed many people are advocating the destruction of those viruses. So that's an even higher level of biosafety and biosecurity. Characterization of natural isolates of H7 and H5 and similar viruses is done in biosafety level 3, which seems to me appropriate. So it's strange to me that we put Ebola in a higher containment level than something which we believe has pandemic potential, although there was some backtracking on that idea today, which I think merits further discussion. So when we talk about the issue of biosafety, as someone mentioned today, it's been traditionally seen as an issue of occupational health. And it mostly is, because most infectious agents are not highly transmissible, fortunately, or we have vaccines against them. In very few cases, including notably the production of highly transmissible or mammalian transmissible forms of highly virulent viruses, it's a public health issue, not an occupational health issue. We accept a certain level of risk of accidents which occur in the pursuit of studies of highly virulent pathogens, because the potential numbers infected are in the ones or tens or maybe hundreds at worst in the event of a very bad accident. That same probability of accident also applies to research with highly transmissible infections, yet the consequences are much higher. And that's why these experiments are in a special category, I think, meriting very special scrutiny. There have been some precedents for laboratory accidents that led to actual public health or animal health impacts through spread. The foot and mouth release from a biosafety level 3 plus or biosafety level 3 agricultural lab in the UK led to a large outbreak in UK livestock. In 2004 in Beijing, there was a release of SARS through a laboratory accident from BSL-3 that led to 2 primary and 7 secondary infections. And most people believe that the evidence points to the 1977 flu that spread, the H1N1 strain that spread for a number of years, 22 years, as being originating in a lab. If you consider infections that don't spread further, there are a lot more examples. Some of them are on this slide. I won't read them all to you, but at least 13 laboratory-acquired infections in BSL-3 in the United States in 2002 to 8. If you take the number of laboratories working on BSL-3 pathogens and you divide the number of accidental infections with the number of laboratory years, so the number of laboratories times the number of years that those laboratories were working, you can get an estimate of the annual risk of a laboratory-acquired infection in a BSL-3 lab. And if you use the data from US select agent accidents, now these are infections, not just exposures, but infections, you get about 0.2% per laboratory year. That's CDC reported data. If you look at the intramural labs at the National Institute of Allergy and Infectious Diseases, NIH in Bethesda, there were 3 laboratory infections in a total of a different denominator, 317 worker years. So that's 2,000 hours of work in a BSL-3. So in other words, if you are a worker at the NIH working in BSL-3, and you spend 2,000 hours or a full-time year, all of that in the BL3, so that might happen over a couple of years, then you have about a 1% risk of getting infected. Those are hard numbers from data. So risk, as the third party is being asked to assess risk, is really the product of probability times consequence. Those levels of risk have been acceptable to people. They've led to some congressional hearings, especially when they're in high-profile labs, but they have been acceptable to people because they have led to very few or no ongoing transmissions. The question before us with this sort of work is whether, when you magnify the consequences to be those of a potential pandemic, then are these risks still acceptable? So to assess the probability, we've done the first part, which is to assess the probability of a laboratory-acquired infection per unit of research. And then we have to multiply that by the probability that such an infection leads to a pandemic. And if you look at the published estimates, there's one specific simulation model from an Italian group of a release from a laboratory in Northern Europe, which estimates about a 5 to 20% risk of that the infection of a flu-like illness, of a flu-like agent, would lead to ongoing transmission that was not controllable. Other estimates can be made from simpler models and put you in somewhere in the realm of 5% to 60%, depending on your assumptions. So when you multiply those together, you get somewhere on the order of 10 to the minus 3 to 10 to the minus 4 per laboratory year of BSL-3 work. And when this assessment is done properly by an independent party with more time, they should consider many adjustments to these estimates. There may be some control measures that reduce these risks considerably, although those are already factored into the Merler study. There may be vaccination or prophylaxis of laboratory workers, which is imperfect but would help. BSL-3 plus may be somewhat safer than BSL-3, although we have little evidence because there aren't very many of them. And molecular biocontainment strategies of the sort you saw earlier mentioned could help, although some investigators fear that they would ruin the experiments and have said they won't want to use them. On the other hand, there has been undercounting of infections and overcounting of lab years in the US Select Agent Program because of the limitations of the way the data are compiled. And as these experiments spread, the standards may not be the same as in the US labs. And this is a quotation from a National Academy report suggesting that there is such global variation. So what about the consequence? The mortality consequence of a pandemic is the expected attack rate of such a pandemic times the case fatality risk times the global population. And I think we're going to agree on the global population to an order of magnitude, and we may not agree on the other two. We might agree on this one. The attack rate of pandemics historically has been 24 to 38% of the global population, roughly within the first year of the pandemic. The case fatality risk, of course, we can't know because we don't know what strain it's going to be. We could consider up to 60%, and I would respectfully disagree with Peter Palesi's claims about the case fatality risk of H5N1 in humans. A large group of epidemiologists published a reply to their estimate that there were millions of missing cases, and I think the evidence for that is quite limited, that basically the H5N1 cases we see are the H5N1 cases there are, roughly. But in any case, we should consider the possibility of an attenuation of the strain. So let's think about 1%. And then the global population is about 7 billion. When you multiply those numbers, you get numbers between 2 million and 1.4 billion fatalities. Of course, many more than the 2009 pandemic, which was a much lower case fatality ratio. But we're talking about taking a strain that is chosen for its high virulence in humans, and which may attenuate or may not. The attenuation results are are extrapolated from a few ferrets, a single-digit number of ferrets. I don't remember the exact number. And it's worth remembering that we're now considering a lower bound of 1%. That's well within the confidence bounds of a few ferrets not dying. Those consequence estimates should also be adjusted. We don't know that the virulence will be even 1%, but they should also be adjusted upwards to consider some of the issues Simon mentioned, about non-fatal losses of health, financial costs, the loss of scientific credibility, even from a small accident after it's been said that this isn't going to happen, school closures, all sorts of things. So when you multiply these together, the risk, the probability of 10 to the minus 4 to 10 to the minus 3 per laboratory year times the fatality numbers, the estimate that you would get if you use these numbers, and I'm happy to discuss why they might be too high, is 2,000 to 1.4 million fatalities in expectation per biosafety level 3 laboratory year. So do an R01 grant for 5 years of running the whole lab. That's a large number of fatalities, which we would never willingly countenance. So either these numbers are way, way off base, which you're welcome to try to claim, and we should discuss, or the mortality consequences are extraordinarily high. And that's the choice. And so far, the advocates of these sorts of experiments have not come up with a single plausible number other than 0, which they admit is not the right number, to say what the risk is. So we need to have a discussion. We need to have numbers. Otherwise, this discussion can't continue in a scientific fashion. In Germany, there is a constitutional right to free scientific inquiry, which is a very special thing that doesn't exist everywhere. And it has been discussed that this sort of considering banning a certain type of experiment is a bar to scientific freedom. I would argue that's not true. I would argue that funders and investigators routinely decide not to do particular experiments, and that is not because they have lack the freedom to do it, but because in the United States at the moment about 90% of infectious disease grants are not funded because the benefits of those grants are too small, or because the approach is not the best way to get the knowledge, or because the budget is not available. Suppose that someone said that these experiments are scientifically interesting and would produce some potential benefits, but they would cost $5 trillion to do. No one would discuss it. We would just say, let's not do them. Lives should be considered in the same way as dollars. And so it's not a matter of scientific freedom. If we decide that the benefits are smaller than the risks, then we shouldn't do them. We also decide not to do things because human subjects protections apply. We decide not to do things because and we prohibit things because animal welfare is harmed too much, or for other biosafety reasons. And even as investigators, we have all had the experience of looking at the data that a student or a postdoc has just provided and saying, you know what, that is not a promising line of research. Stop doing it and do something else. That's not abridging their freedom. That's making wise scientific discussions. And it might not be just that's not going to teach us anything. It might be, well, we could do this, but it would cost us half the budget for the year, and we don't have that much budget. We make these decisions all the time, and lives should, if anything, be more important than dollars in these kinds of calculations. So how should we frame the choice? I think one way it's been framed, which is indeed very hard to get one's mind around, is to ask the question, do we do the experiment or do we not do the experiment? Do we allow gain of function or do we not? And the problem is that that's not the way anyone makes real decisions. In the lab, we don't say, your experiments are going nowhere, stop doing it and go play golf. We ask them, we say, your experiments are going nowhere, stop them and do something more promising. That's also how economic choices are made. We decide we're not going to spend money on this, and so we'll spend it on that. And there are a number of ways to study and defeat influenza that are not dangerous. In fact, virtually everything except for the 18 studies, and probably even some of those are not very dangerous. Other than those 18 studies that have been identified in the US, the NIH's portfolio contains essentially no dangerous experiments. It contains a lot of very promising experiments, about 200 plus R01 grants to do flu experiments, for example. And all of those combine a very low or negligible risk to human life with several desirable properties, such as often lower cost because of the high cost of doing ferret work, the low throughput and statistical power necessitated by using 3 ferrets or 2 ferrets per experiment, and therefore the lack of generalizability because you can't use very many flu strains. Some of these are ways of trying to get at similar questions, and I take the point from the advocates of this work that there are certain questions we can't answer without gain of function. You cannot answer the question of, can this be transmitted in ferrets without making it transmit in ferrets? That is true. But you don't have to understand the enemy to defeat it, and our goal is to defeat flu, not to understand it for its own sake. We would like to do both. But there are other kinds of understanding that may get us to a similar place. We were told this morning, that, or earlier this afternoon, that we knew nothing of what was required for transmission before gain of function. That's not true. The original experiments engineered in several mutations that were thought and indeed proved to be important in the polymerase and the hemagglutinin. We've also seen all of that was known before gain of function. We did learn one more phenotype that was important, but it's not true to say we knew nothing. There are other ways to find out these related questions, and there are other approaches, like the universal vaccine approach you just heard about. So there are lots of things we can do, and only some of them require science about flu, and only some of those, namely the 18 studies or fewer, require putting the public at risk. So what about benefits? I think this is the hardest one, but I think it also can be thought of more clearly if we take into account the position of the decision maker rather than a sort of abstract position of should we do this experiment or not. So on this slide, the square is meant to be a portfolio of research approaches and other approaches to trying to defeat flu. So this is our investment in flu prevention and countermeasures. And you could compare the benefits of a portfolio including PPP, or potential pandemic pathogen creation, alternative approaches to flu virology of the sort that I had on the last slide, and surveillance, universal vaccine research, host-targeted therapeutics, other ways that are not flu virology but are still important ways of trying to defeat the flu. The appropriate comparison, as any health economist will tell you, is to keep your budget constraint the same and allow for the opportunity cost that spending some of that on PPP work imposes by comparing it against the same amount of resources spent on the alternatives alone without the PPP. We should then weigh which of those is greater and see which way which it favors. But there's an additional aspect which only the PPP experiments have, which is the risk. And the risk I've tried to describe. I think it's, if you put it in monetary terms, would be so outrageous as to be discussion ending. But somehow, because it's lives and it's hypothetical future lives, it seems to be maybe more acceptable to some. You would weigh the risks of the alternatives as well, but those alternatives have no such risks, at least negligible risks by comparison. And my view is that the benefits of an alternatives portfolio will be much greater, especially when the risks are taken into account. Ethical reasoning also brings us actually to a remarkably similar point. I said that in a health economics framework, you would weigh a portfolio of one set of approaches against a portfolio of another with the same budget, because you want to compare apples to apples. Remarkably, the Nuremberg Code, which is one of the leading, probably the most important document in bioethics of this century, but is not directly relevant to PPP experiments, pushes us towards ethical principles that say give the exact same idea. The green highlighting is mine. There are two principles in the Nuremberg Code that I think are relevant. when you are going to put a human subject at risk by giving them an experimental drug, for example, the Nuremberg Code states that the experiment should be such as to yield fruitful results for the good of society, unprocurable by other means or methods of study. So it implies that we should be doing comparisons against other potentially less risky approaches. And it also states that the benefits should be measured not purely on a scientific scale, but on a humanitarian scale. You should not put large risks on people unless they have comparably large humanitarian benefits. As I said, the Nuremberg Code does not apply to gain-of-function work. It is about human subjects. It's very clear what its application is, and I would not suggest that it currently applies. I would suggest that the ethical principles that we've all accepted and live under when we deal with human subjects derive not from the fact that there's a person in your experiment that you can point to, in your clinical trial that you can point to, but from the fact that people are being put at risk. If you agree with that, then you will agree that ethical principles like those underlying the Nuremberg Code should apply to the evaluation of experiments that put humans at risk, even if they are not identified humans who are in the study itself. And these include seeking lower risk alternatives and requiring not just a scientific good, but a social good when humans are put at risk. The other benefit of looking at it in this framework is the sort of blue sky argument. It is true that we do science in part because scientific pursuits lead to benefits we never imagined. The discovery of bacteriophage restriction systems was the beginning of molecular biology, and it was a sort of backwater, fascinating area of basic science that was nobody thought was going to spark a multi-billion-dollar industry and create vaccines and all sorts of great things. There are lots of reasons to do science that we can't anticipate and that we can't quantify. But nobody is suggesting do less science. The only question, as we do every day in the laboratory and as funders do every year, is do we do this mix of science or that mix of science? And the blue sky benefits of the things that we do with the money we could have spent on PPP should be just as great as those of the PPP experiments.